All right. Hi, everyone. My name is Sasha Zelenovic, and I manage Red Hat's AI developer marketing and developer advocacy teams. I've been co-hosting these office hours with Michael Goin, who is a principal engineer at Red Hat and also a vLLM commuter for these sessions now. So I guess congrats to all of us. Thanks for keeping this program going over the last year and a half or so. It's been a busy January. Typically, these office hours are a bi-weekly session, but it's been a weekly session in January, and it's probably looking like that in February as well. So I think you guys definitely appreciate a lot of the content. So we'll be communicating all of the upcoming sessions in the next slide, but also in the coming weeks as we solidify more of them in February and in March. Today, we're really excited to join Fynn, Helen, and Rahul. Fynn, Helen, and Rahul have been doing a lot of things, but one of the things they've been working on is building, distributing, and maintaining the Speculators library, which is a unified library building spec decoding algorithms with vLLM. So I think we have a great team here. They're very hands-on, and they'll tell you all about speculators. So feel free to ask questions and provide any comments or suggestions for the project. So in terms of upcoming sessions, today, as I said, we're talking about speculators. Next week on January 22nd, in 7 days on Thursday, we'll be giving you a LLM compressor update. There's a lot of good stuff that's been contributed and added to the LLM compressor. So it's a pretty exciting one. If you are not familiar with LLM compressor, it's an open source library that's part of the vLLM project that lets you optimize LLMs for faster and efficient inference at a very high level. Google LLM compressor to dig deeper, but we'll also do a very deep dive sharing the features in the next Thursday. And then after that, we'll be diving into the vLLM CPU offloading connector. That's on January 29th. We do record all of these sessions, as you probably see. You can always find them on YouTube. So feel free to forward, watch again or forward your colleagues. All the slides are linked in the YouTube videos, so you can always reference the slide as well. And if you can find something, you can always reach out to me. With that said, Michael, what's going on? What's going on in the vLLM community? How's your week going? I know we spoke a week ago, so I don't think there's going to be as much as last time, but share something with us, please.
Yeah, definitely. Thanks, Sasha, for kicking us off, and really happy to be back here for everyone and for this great guest topic. Yeah, there's been a lot of progress in vLLM. We were hoping to have 0.14 release this week. We're still working through the final push and release candidates for that, but we're close over the line. We'll definitely cover the release in the next one. But for now, we'll just go over some general updates in the community and things around vLLM. With that said, let's go ahead and get started. So as you hopefully already know, vLLM is the high throughput, memory efficient inference and serving engine for LLMs. It's Apache 2.0, permissively licensed, adopted by hundreds, if not thousands, of companies and academic institutions as the de facto standard for production LLM serving. It's a very popular project in open source itself, with over 65,000 GitHub stars and hundreds of pull requests that we happily review and merge every month. We have hundreds of thousands of GPUs deployed 24/7, resulting in millions of hours of GPU deployments every day. And we have a very diverse group of contributors. Over 2,000 people have contributed into the vLLM repository itself, not counting all of the projects and diverse ecosystem around it, like LLM compressor and speculators that Sasha's already mentioned. And of course, we have that across a diverse group of companies, academic institutions, frontier research labs. So hope you have merged code in vLLM yourself, and if you haven't, consider giving it a try. And so part of the reason why vLLM has become such a popular and industry standard for serving LLMs is because of its ease of use, and both in being able to install and easily serve models from Hugging Face or other model repositories, supporting over hundreds of different model architectures, and supporting, most importantly, the state-of-the-art models when they come out on release date. Especially a lot of the recent ones like GLM and MIMO and long cat flash and DeepSeek models, GPT-OSS, and so on. We can run those models efficiently, not just on NVIDIA hardware, but across a variety of hardware support that you can already see detailed here, even some more hardware backends than this that I need to update this continuously. And then running those models across more than just one device, but across multiple devices within a single node, or even across multi-node deployments with several different types of parallelism, coming from what we hear in the field, and as large-scale users of vLLM scale up their usage. And as I already mentioned, vLLM is as a project is not just vLLM itself, but a diverse ecosystem of projects like vLLM Omni, GuideLLM, Semantic Router, Production Stack, LLMD, and we're constantly growing the ecosystem of projects within the vLLM project, not to mention all the open source projects that build on top of vLLM as that abstraction layer for LLM inference. So as I mentioned, we unfortunately don't have a release to cover this week, but I do have some blogs and things for you to check out. First off, we have a new official KV offloading connector. Specifically, this is for native KV cache offloading to your local CPU on the same vLLM instance. We've supported, obviously, KV cache offloading with other integrations, LM Cache and Mooncake, or for disaggregated PD, like with Nixel. But now we have a native async implementation that's performant and has some custom kernels in itself. So there was a blog on this. And if you really want to know more, we'll have an office hours on this at the end of the month, January 29th, to hear from the authors themselves on the work they did to do this. So yeah, look out for some fun numbers and algorithms to go through there. Next, I want to call out the continuous great work that the Unsloth team does to make reinforcement learning really approachable and easy for people to train state-of-the-art RL models and experiment with these on more accessible hardware than clusters and clusters of GPUs. And they've really been pushing far on long context RL. Just recently, pushing like 7 times longer context on here on GPT-OSS and Qwen dense models. So you can run these on single H100s, which is pretty cool. Yeah, if you're interested in exploring reinforcement learning, Unsloth is a great starting point for hopefully experimenting not just on H100s, but also even L4s or your local 3090s or 4090s. Next, I want to cover, we've had quite a bit of RFCs over the past weeks. There's been a lot of sort of refactors and large roadmap items that we want to cover and talk about more broadly with the community and in the spirit of being open and inviting as many people in. And these are the ones just over the past week that I want to highlight, covering a pretty wide variety of topics. We have sort of online quantization and the pause and resume APIs. Both of these are really important for large scale reinforcement learning workflows where you're constantly updating the weights or needing to re-quantize the weights inside of vLLM as you're getting new weight updates from your training process and going between the cycle of training and inference constantly with reinforcement learning. So we're really happy that different organizations are getting involved in improving the quality and flexibility of vLLM for reinforcement learning. And then towards custom ops and how we integrate and manage the complexity of many different optimized kernel implementations in vLLM. We have a really great recent RFC from Luca on our team, who's done a lot of torch compile work inside of vLLM, where we want to now define a vLLM IR or intermediate representation. Ultimately, a better wrapper for the custom op integration, if you've seen that before, with some interesting ideas of how we want to support this to support multiple hardware platforms, multiple kernel DSLs and implementations, and how we manage that complexity and give a nice front-end interface to model developers and also users of vLLM. And also in tandem with that, Helion is a new library or domain-specific language from the PyTorch project that's essentially trying to be the middle ground between PyTorch and Triton. So if you write Helion code, it can start to automatically get fused with surrounding PyTorch code. So effectively just getting better support for Torch compile inside of vLLM, and hopefully getting more kernel fusion for free. And there's a lot of goodies in there, and benchmarks and things for how the Helium integration is already going, and what our hopeful plans are for making it a first-class citizen in vLLM over the coming months. So there's many more RFCs than this. I highly recommend checking out the link at the top. Your comments and inputs and interest in RFCs are really appreciated, because it directly influences where we spend the majority of our time, considering and pushing and fostering these new ideas between the lovely people that have written up these proposals. That's all I have to cover today. And I want to hand it off to the lovely speculators folks. Take it away.
Yeah, so I think we can all start by just introducing ourselves. My name is Fynn. I'm part of the model op team at Red Hat. And yeah, I'm a machine learning engineer, and my main focus right now is on the speculators library, which we'll be talking about today.
I'm Helen from the same team. I'm also working on the speculators.
Hi everyone, I'm Rahul. I'm a machine learning engineer at Red Hat, and I work alongside Fynn and Helen on the Speculators project and some other things that we've built out recently.
Awesome. Let me walk through the content table briefly. We're going to start with a speculative coding intro, followed by an intro to speculators, our own repo, then data generation and training for Eagle 3 draft model, and finally serving in vLLM. So what is speculative decoding? It's a lossless technique to speed up LLM inference by using a draft model, the speculator or small model, if you want to call it, to speculate and propose tokens. Proposed tokens are later verified by a larger base model, the big model, or what you were trying to serve originally, which verifies the token in a single forward pass. It boosts performance without sacrificing quality. You can think about it this way. Draft model is responsible for doing the heavy lifting. Most times we're generating very easy tokens like D, A, and of. It probably doesn't take a 235B model to speculate that. So the draft model intelligently drafts multiple tokens ahead of time for the base model to verify. Every accepted token is guaranteed to come from the same distribution as if it was generated model directly. So how does it work? I'm going to explain by a comparison between vanilla versus speculative decoding text generation. In vanilla text generation, we run a forward path followed by a decoding phase. We get the tokenized text input, feed it into a large language model, and we get back a potential token probability distribution. And we go through the decoding phase and get a generated token, which is then feedback to input sequence for next token generation. This process is fully sequential. We only, for one run of the model, we only generate one token. So how does speculative decoding actually speed up this process? With three main steps. We have the token speculation, the parallel verification, and rejection sampling. In token speculation, the draft model generates k predicted tokens. For example, in this input sequence, what color is the sun? When k equals 3, draft model speculates the next 3 tokens. You can see the distribution here. It is orange. And then the base model concurrently verifies the draft model's output with the assumption they're indeed correct. We can see the draft model speculates it is orange with this probability distribution, and we feed it back to the base model. And the base model then verifies with its own distribution. We not only get the base model's confidence for the previously speculated tokens, we also get the next predicted token. And finally, we come to rejection sampling. We can either reject or accept the token based on the draft model's probability and the base model's probability. We can see here the base model is fairly confident that these two tokens are probably good, but it's less confident in the token generated by the draft model, the orange token. And then we can see this model is then rejected by the base model, and everything generated after that would be discarded. As a quick recap, we can see here are some pre-fill tokens, and then draft model would auto-regressively draft 3 tokens, and then in parallel, the target model would write tokens. We can see the base model again confident about the 1 token up, but is less confident about model and inference. So these 2 tokens are later rejected. But we still get the generated token sampled from target distribution from the base model. So even in worst case scenario, all speculated tokens are rejected. We still get at least 1 token generated from the base model. I'll hand it off to Rahul to talk about why use speculative decoding and when to use it.
Thanks, Helen. So the next question is when to use speculative decoding. But even before we start answering this, we need to understand 2 important factors when it comes to LLM inference. Number 1 is the time spent in data movement. That is the time it takes to load the weights from the VRAM to the actual computation cores. And second is the time spent in doing actual compute. Now, modern GPUs are very, very efficient at math operations, which means in low batch size regimes, when they have less work, they are essentially idle for a lot of time. And most of the time is spent in this data movement. It is places like these where speculative decoding can prove to be beneficial. When these GPU cores are idle, then speculative decoding trades this pair compute for memory bandwidth and essentially use this time to run forward passes through the smaller model and hence give us speed up. On the other hand, in high batch size scenarios or in scenarios where we have a lot of queries per second, the GPU already has enough work. So in these cases, the speculative decoding process, when it adds more compute to run the smaller draft model, it's not necessarily true that we'll see the benefits out of that. And actually, in practice, it may even turn out to be slower than vanilla autoregressive inference. If we look at this graph, this is a graph generated by our team, and we test a Llama 70 billion model with vanilla autoregressive inference versus inference using speculative decoding. And we can see here, the blue line is the one using speculative decoding. Red line is the one that's just vanilla autoregressive inference. For low queries per second regime, we actually do better. But there is an inflection point after which the process becomes compute bound, in the sense the GPU is already saturated with a lot of work. In those cases, speculative decoding can prove to be much lower than vanilla autoregressive inference. This being said, all I want you to take away from this slide is that speculative decoding is not a universal solution. It can help us in some regimes, but not for everything. When we have latency sensitive situations, such as user-facing applications, using retrieval, augmented generation, or agents or assistants, mostly these applications will produce a longer response to the user. And in these cases, speculative decoding can prove to be beneficial because it essentially speeds up the generation, and latency is what we care about. But on the other hand, if we have a throughput heavy situation where multiple requests are being bombarded onto the GPU, in those cases, the speculative decoding trade-off might not be as beneficial to us. Another point to note is that if we have a situation where we expect the LLM to produce short answers, for example, multiple choice questions, in those cases, too, speculative decoding might not be as beneficial because it does not improve time to first token, but it improves inter-token latency. So just a rule of thumb, if you expect your application to produce smaller responses, maybe speculative decoding is not the way to go. If your GPU is being bombarded by many, many requests and it's always saturated with work, maybe don't use speculative decoding. But if latency is what you care about and your inference or the application is memory bound, then use speculative decoding. Then, I mean, there's so many things we said that, hey, don't use speculative decoding here, don't use speculative decoding there. Why should we use speculative decoding? One of the best advantages, in my opinion, of speculative decoding is that it is lossless, which means the output produced using the speculative decoding process is the same as if you were using vanilla auto regressive inference with just a verifier. So the quality of the output does not take a hit at all. Secondly, speculative decoding is orthogonal with other optimization techniques, which means you can combine quantization or sparsification along with speculative decoding. We can quantize both the draft and target model, which can give us more speedups. It is also orthogonal to other acceleration techniques in the sense if there's a new attention implementation tomorrow, which is faster, speculative decoding should be able to use that. And then when used in the right regime, it gives us a very decent speedup by essentially using our GPUs more effectively. These are some more technical points to what I said before, but essentially speculative decoding helps speed up the process by getting more work done for the same data transfer cost. It helps us utilize idle hardware when the GPU is busy with data movement, when essentially the data is being moved from the VRAM to the compute cores and our GPU cores are sitting idle. Speculative decoding uses this free compute to run forward passes through the draft model and gives us faster generation. And in the end, in turn, it also increases arithmetic intensity by increasing the ratio of math operations per byte loaded. So speculative decoding turns idle GPU compute into a shortcut through the memory bottleneck, thus reducing latency, given that the system isn't already saturated with requests. These two graphs were generated by our team. Both the models were generated using the Speculators library, and we tested them across a range of query per second scenarios and measured their latency. In these graphs, dark blue is better. The blue color here shows the speed up against auto-regressive inference without using speculative decoding. For both the models, one on the left is a Qwen 332 billion model, one on the right is Llama 370 billion. For both of these models, we see that in low request per second scenarios, our models using speculative decoding give us at least 2 to 2.7x speedup, which is very, very good. Now we tested the same model across different tasks. We used it for coding, math reasoning, and summarization. Across all these three tasks as well, we can see that for low request per second scenarios, we get the best benefit. And then if we look at the left graph, as the request per second increase, then we hit an inflection point after which speculative decoding process is actually slower or does worse than vanilla autoregressive inference. And in all these cases, we got a speed up of at least 1.7x in low request per second regimes. With this, I hand it over to Fynn for the next part of the presentation.
Yeah, so thank you, Rahul and Helen, for introducing speculative decoding and also explaining when and why we might want to use it. I'm now going to talk a little bit about the Speculators library, which is kind of what we've been working on for the last year. And what we're trying to do is create one place for all these different speculative decoding algorithms that exist out there in the greater community, the research community. One place where we can have strong implementations of them and strong training and converting code, so that if you want to create your own speculative decoding model, it's easy to do so. And so that's kind of how Speculators, the library, was born, and we created this tool. It's very easy now to train new models. And one thing I should note with speculative decoding, because we want our draft models to the tokens they propose to be accepted by the verifier model, it's usually important that the draft model and the verifier model are closely aligned. And so what we usually do for that is we train a draft model that works specifically with a specific verifier, so that it learns the verifier's kind of probability distributions. But we make that easy to do here with the Speculators library, and in a way that's where we're outputting checkpoints in a safe transfers format that has also a config that makes it super easy to run these models then in vLLM. And Rahul's going to talk a little bit about how to actually run them at the end of this presentation. But to start, I want to talk a little bit about, or you might be wondering, what models am I talking about? And the one we're going to focus on today is an algorithm called Eagle-3. And Eagle-3 is kind of one of the big state-of-the-art algorithms for speculative decoding right now. And it's usually implemented using actually a very small model, usually just a single decoder block layer. But it's still able to get good performance and get good acceptance rates relative to the verifier, because it kind of almost hooks into the verifier model and takes hidden states from multiple different levels within the verifier as input to the model. And this kind of gives it a lot of context about kind of what the verifier model, which has a lot of layers, what it's thinking, allows it to predict not just the next token, but also a few tokens in advance with relatively good accuracy. But as you might imagine, for inference, we use vLLM, which has support for this, and gets these hidden states and passes them to the Eagle-3 model. But in order to train a model like this, we need to have access to kind of a data set of hidden states, plus their corresponding token IDs and the targets that we want to use during training. And so we need a way of getting these hidden states from vLLM and getting them out so that we can create this training data set and train our models, so that we can eventually get that 2x speed up that Rahul was talking about. And so Helen's going to talk a little bit about how we use vLLM to extract these hidden states for training.
Thanks, Fynn. Yeah, turns out hidden states generation and offline data generation pipeline is a non-trivial part of the training process. So how do we actually prepare these training data for the Eagle-3 speculator models? Let me start with just a quick overview of what we'll cover. First, I'll explain what the hidden states generator is and how it works. And after that, I'll show you the architecture and key components. And finally, we'll dive into our offline data generation pipeline, a 3-stage end-to-end process for preparing a training data, actually train a draft model. So what is the problem here that we're trying to solve? When training a draft model for speculative decoding, these draft models need to learn the target model's internal representations. We want the draft model to think like the base model, so they require hidden states from the base model as intermediate layers. The challenge is doing this efficiently and making it scalable for production data sets and very large models. We're talking about like a Qwen 235B models and possibly even bigger than that. Our Our solution consists of two main components: the vLLM hidden states generator, which captures hidden states during the prefill phase, and an offline pipeline that automates and makes this entire data generation process reproducible and robust. It's optimized for multi-GPU setup and large-scale models. Let's talk about vLLM hidden states generator. This is the core component. You can find this in our code base at vLLM hidden states generator.py. Its main job is to extract intermediate layer hidden states from the base model using vLLM's inference engine. A few key features: it's prefill only. It supports tensor parallelism for handling those really large models, and it does batching processing with multi-process execution. The interface is pretty straightforward, as I showed here. You initialize it with your model path, and optionally specify which layers you want to capture. If you don't specify, it auto-selects 4 key layers based on the Eagle3 paper, which our research team uses. And you can configure tensor parallelism and GPU memory utilization, just like you can in vLLM. The output for each sample is a dictionary containing the input IDs of the input tokens and a list of hidden states that you specified, and the loss masks that tells us which token to train on and which token to ignore. How does it actually capture these hidden states? This is where things get interesting. I'm showing a diagram of the generator workflow. The generator creates an executor and a scheduler, makes and adds requests to the scheduler, who then queue and batch up these requests and send to executor. The executor then spins up several custom worker of RPC calls to set up hidden states capture. And the custom worker extension will capture hidden states and return via RPC calls as well. Let me move on to the custom workers and how that works. We use vLLM's extension system. In the parallel config, we specify our custom worker extension class. That's the hidden states worker extension. What this does is vLLM loads our extension, and the extension patches the forward pass at runtime. During inference, it captures hidden states at the layer that we specify and stores everything in GPU. It is completely non-invasive. We're not modifying the model source code at all. It's multi-GPU aware. We only capture tensor parallel rank 0 to avoid duplicate. And it's memory efficient through batching process and async saves to disk. And finally, let me talk about the whole offline data generation pipeline to prepare our training data end-to-end. Stage 1 is data pre-processing. You can find it in preprocessing.py. We load the data sets. ShareGPT and AltaChat, for example, are supported natively. You just have to pass in a string. Or you can choose to pass in your own data sets as long as they're in the correct format. We apply the tokenizer's chat template to properly format the raw conversations. And then we generate the loss masks. These are binary masks, where 1 means train on this token because it's generated by the base model for assistant responses, and 0 means mask out this token because this is generated by a user, or it's just a system token. We also compute token frequency distribution, which we'll use later for vocab mapping. This is used because we're usually training on a reduced vocabulary. Everything is cached using Hugging Face fingerprint-based system for efficiency and recovery if the process is ever interrupted. Stage 2 is the hidden states extraction, which I just talked about, using our vLLM hidden states generator. And stage 3 generates configuration and metadata. We create a dataconfig.json file that contains the full reproducibility information, the exact command that's used, all the package versions, GPU information. We also save a token frequency.pt file for vocab mapping. And all this is to ensure that we can reproduce all the results exactly. So now we have the training data. I'll hand it off to Fynn to talk about the training process.
Thank you, Helen. Yeah, so I'm going to talk a little bit about Eagle 3 model training. So to start, I want to actually give a little bit of a recap on just general large language model training and kind of some of the considerations that come into play with it. So typically with large language models, you have your token sequence as an input here, and for every token that you input, you're actually predicting as output some kind of probability distribution. And for inference engines like vLLM, typically we kind of just ignore all of the output probabilities except for the very last one, which we use when we sample our next token, and then we add that to the token sequence and repeat the process. But for training, we want to actually take advantage of the fact that we have this probability distribution for every single output. And what that probability distribution is kind of the probability of the next token given the prefix of the sequence up to that stage. And so we can use that to, in parallel all at once, train, based on T1, predict T2, based on T1 and T2, predict T3, and so on. And so this is kind of what that looks like. We're comparing the probability output distributions with the ground truth next tokens. And to kind of show that in another way, here are kind of all of our different sequence prefixes, so potential sections, and we have that probability output from the model, and we're feeding that into, we're writing a loss function that compares that to the ground truth next token, and we use that to generate a loss. And for distillation, when you're training a model based on another larger teacher model, this process is similar, but instead of using the ground truth next token as your target, you would instead compare the teacher model to the student model, the probability distributions between the two. And so that's actually kind of what we're using during speculative decoding training, is we want to use that kind of distillation technique as well, so that we get our drafter model to be as similar in kind of its probability distributions to the verifier model as possible. So that's a quick recap of general LLM training. And now for the Eagle 3 algorithm, we kind of have a few special considerations to make. So to start, there's this algorithm that was introduced in the paper called training time test, which is kind of a training time augmentation that allows us to get better performance at drafting not just the first token, but actually a few tokens in advance. And the way that it works is it kind of simulates the drafting process during training. So as you're training, here we have these input sequences, so how can I, and we generate for every prefix sequence, so how can, and how can I, we generate a next token draft. And then we repeat this process a few steps. So then, there's a configurable parameter, a number of TTT steps. And so in this case, we have 2 steps, and we draft 2 potential next tokens for every prefix of our sequence. And then we're computing the loss for the first token prediction, the second token prediction, and so on with the ground truth labels that we have. And so the result of this, as you can kind of see here, it kind of changes the attention mask that we're using, and kind of has some affects some considerations when we're about how we set up a training loop. And then the other thing I want to talk about is how we actually train these sequences when all of our sequences are kind of different lengths. And so, this is a problem that's common with all large language model training, where our sentences or input sequences are different lengths, and obviously that doesn't work well for matrix multiplications and so on. So we need to do something about this to make it more uniform. And kind of the most straightforward approach is to just pad all of our sequences in a given batch up to the max length in that batch. And this certainly works, and you can train your model this way. Except obviously we have now a lot of padding tokens that we're creating, and there's some intelligent things we could do about like which token or which sequences end up in which batches, but we're still from the model's perspective, every padding token it doesn't know which ones are padding and which ones aren't. So we're doing the same amount of computation for every padding token, and then at the end we're discarding the result from it in our last mask. And so that's a lot of wasted computation. And if we can save some of that computation, fit more sequences in the same batch, then we can speed up our training process overall. And so kind of the other approach to this problem is instead of padding our sequences, we can pack them. So what this means is you basically just concatenate them all together into one long sequence. And then, you might be concerned that okay, now sequence B, part of its prefix is sequence A, and is it looking at the wrong sequence? And the way you handle this is just using attention masking to kind of get all the sequences to be treated, again, as separate sequences. So that's what I have here on this next slide. We have a quick example of, here are a few different sequences. Each sequence, the tokens in each sequence only attend to other tokens within the same sequence. And in reality, our attention mask doesn't look quite like this. It looks more like this, because we're also using causal attention models. And so each token only attends to tokens in the same sequence that came before it, and none of those that came after. So this is a little bit what our attention mask looks like. And now if you remember from the training time test page, there's also this extra step where we add kind of these diagonals, which looks like this. So after the first step, on the very first step, our attention mask looks like what I had on the previous page. After the first step, it looks like this, where on the left here, all of our queries are the kind of next sequence draft. So A1 star is the next token that was generated after A1, that was drafted after A1. And yeah, we use the KV cache to store KV values from the previous step. And then this is kind of what our attention mask looks like. And so kind of all of this TTT and sequence packing and so on, all of this can kind of be implemented through kind of clever configuration of the attention mask that we use. However, now you might notice looking at this that this is a very sparse looking attention mask. And now we have a new issue, which is we're wasting a lot of compute if we're computing this empty region and then just masking everything out, and same for these other regions. And usually you would use like a flash attention kernel or something like that, which would have support for causal attention with multiple sequences packed together. Except because we have this unusual extra diagonal, we can't directly use that. And so we're using flex attention here, which comes from the PyTorch team. And this makes it kind of really easy to define just a mask function where you can specify kind of which components of the attention mask or the attention matrix that needs to be computed. And PyTorch will kind of, once you torch compile it, will go through block by block and determine if a block needs to be computed, and if not, it just skips it. And so we found that this leads to a very fast and memory efficient implementation for our training library. Yeah, and so those are kind of the main features. I want to also very quickly highlight a couple of the other features which are important. So, I mean, obviously we need some kind of distributed training to speed this up. And so we're using FSDP, which copies our model onto each GPU and speeds it up that way. And we also use automatic mixed precision with it, which again allows us to, we do our forward passes kind of in low bit, or like in smaller precision, and then our gradient accumulations in higher. And this just speeds the process up. And we also have this multi-backend metric logging. So we log all our loss and acceptance rates and so on to console, but you can also choose to log to weights and biases or track IO or TensorBoard, whichever you prefer, or some combination of them. It's just a selection option. So yeah, those are kind of the features. And you can use this to train your own models, and please do, and please let us know how it goes. And now Rahul is going to talk a little bit about how to actually use these models that we've trained in vLLM.
Thanks, Fynn. So how do we use speculative decoding in vLLM? For that, first we need to answer the first question, which is to find the right drafter. To do this, you can either train your own drafter on top of the verifier. Eagle3 does that. You can use speculators to do it. You can convert existing drafters into the speculators format. Existing drafters being the ones created using research repositories. We have conversion tools available in speculators as well. Or you can go to Red Hat AI's speculators collection on Hugging Face Hub, where we've already trained many Eagle and Eagle3 speculators for you to use right out of the box. Once we've selected the drafter, then if it's in speculators format, then deployment is as easy as a simple command, vLLM serve speculator model. And let's say if you're not in speculators format, or you just need some more fine-grained control over the deployment process, then you can use the long form of the command, which takes in a speculative config. And this can be used to like experiment with different verifiers, maybe swapping in, let's say, a quantized verifier against instead of the base one, or changing the number of speculative tokens being produced by the drafter, and other things like that. Once the model has been deployed, then for evaluating the model on performance benchmarks, you can use something called guidellm. It is a tool that our team has built out. It's a part of the vLLM project. And if you run a command that looks similar to this, you will get the expected speedups and performance number. Development is going on at full swing in the speculators repository. We're working on a lot of newer features. A few things that we want to support in the future are online hidden states generation through vLLM directly. Then we want to add support for vision language models. And we also want to expand our support for different algorithms, including MTP and DFlash. That's pretty much the end of the presentation. If you found anything interesting, please go check out the speculators repository, go look at examples, comment on issues. If there are any new drafters that you would like to see for your use case, put up a good first issue there and we'll be happy to help. If there are any questions, we are also fairly active on vLLM Slack channels, speculators and feed spec decode. So you can reach out to us directly there. And we built out the repository in such a way that there are a lot of examples and starter scripts for anyone to there's just simple commands that you can run and see speculative decoding in action. Do start the repo and reach out to us. We're more than happy to answer any questions and help you in your speculative decoding journey. Over to you, Michael.
Yeah. Great job. It's that I can definitely tell by the activity that there's a lot of interest in this space. Yeah, I mean, just a great overview. Maybe like a good thing to cover first before we get into some questions is how do you see people using the project and the models already? Do you have any like production usage or users of the project?
Well, we do have a lot of people. Oh, sorry, Fynn. Go ahead. Take that question.
Well, if you have a comment, you can go ahead. Didn't mean to cut you off.
So we do have a lot of people using speculative decoding. Right now, training support is fairly new. Our internal research team has been the first user of our training pipeline. And all the graphs that I showed during this presentation were generated using the speculators library. So the models that were produced using the training pipeline there. And they were benchmarked using guidellm. And yeah, Like there's been a lot of community usage and usage from other bigger enterprises, but it is a growing repo. We want to see what the community wants from us, and we're more than happy to build that out.
Yeah, great. I mean, kind of towards that point, where do you think like external people in the community can help the most in the project? There's obviously a lot of things to work on, but is there a section that's maybe easier to get started?
Oh, absolutely. So if you go to the Speculators repository, we have a lot of good issues. That is one place where people can contribute if they want their PRs to get merged in. Otherwise, if they have a general use case, they can just create an RFC, or they can create an issue themselves and one of us will respond.
Yeah. Okay. Sure. Fair enough. I can see you guys are already answering questions in the chat. Are there any you want to respond directly to in voice, or people that want to come off mute? Yeah, I thought someone raised a hand earlier. Maybe close it down. I'm not sure. Yeah, what are the plans to overcome high RPS region where speculator gain diminishes? Yeah, I mean, I know from the vLLM side, this has been like a continuous issue and project. I think one of the first vLLM office hours actually was kind of on this when we first covered speculative decoding by Lily Liu. Yeah, I think it's more of a, how do you implement this efficiently in vLLM, right? It's hard to dynamically change like the batch size or padding. You have a lot of things like CUDA graphs and scheduling decisions yeah. And then of course, how do you decide the threshold of when you should start to decrease your number of candidate tokens because your, just request batch size has gotten large enough? There's like I remember seeing a PR like yesterday on this actually that seemed like pretty promising. So yeah, there's definitely appetite for this, and I think we're at a pretty good place now to start considering this. But yeah, I mean, towards that point, I think it's like kind of fully on the vLLM side to resolve and make that efficient. And from the speculator side, they'll just keep making models with better acceptance lengths, so we can get better speedups where we can.
Yeah, and I just want to add to that. As you mentioned, the PR yesterday, I think I also saw in vLLM Slack, yeah, just today that someone was posting. They've created like a dynamic implementation that is not perfect, but it allows you to kind of reduce the amount of speculation you're doing as your batch size increases, and that alleviates a lot of kind of the overhead from speculative decoding in those high batch size regimes. So it's not perfect. It's still slightly more expensive once you get to a large enough batch size, but it's certainly a step in the right direction to kind of make it be something that you can kind of always have on, because it kind of automatically mitigates overhead when needed.
Yeah, exactly. You found the PR. Yeah, any other questions people have or that we didn't get to?
Yeah, so someone was also asking about different methods to use, so Ngram versus Eagle 3 and so on. I mean, Eagle 3 is kind of one of the ones we found has kind of some of the highest performance, but the disadvantage of Eagle 3 is you have to go through this process of training a new draft model for it, which we try to make as easy as possible, and there's also a lot of these kind of publicly available on Hugging Face, but there are situations where you might want to just go with a solution like Ngram, where I think that's a model-free solution, and you can just kind of deploy that right away. yeah, but it kind of, and there's also new implementations, new algorithms kind of coming out as we progress. So certainly what's the best algorithm to use, it depends on a lot of factors, and there's no like one answer there.
Yeah, okay, sure. Also, one thing that I didn't really see covered here, that's something I still don't understand well, is like is tree attention used now for the Eagle training, or I think not inference, but yeah, is that like a future thing to consider?
No, it's not something we're currently using. I haven't looked into it too much in terms of if it gives us benefits during training, because I think for training there's a lot of different considerations versus like inference time. But yeah, it's not something we're currently using, and currently we're able to get flex attention to work quite well.
Yeah, cool. Well, yeah, any other questions or discussions we should go over? No? Okay, I'll take that as last call. Well, thanks everyone for coming to the office hours. Really, really appreciate Fynn, Rahul, Helen for the great overview on speculative decoding and speculators. And thank all of you for being a part of the vLLM community and coming to these office hours. If you want to get involved, you know where to find us. All the things are here. And we'd love to see you again. And see you in next week, not just 2 weeks. We're packed this month. So hope you have a good week. And yeah, catch you then. Take care, everyone. Bye-bye.
See you.
Thank you so much.